All right, welcome students. This explainer is your study guide for Unit 5, and we're tackling a big question. How does treated water get all the way from the plant to your tap? It's a fascinating journey, and we're going to cover everything you need to know. I mean, think about it. You turn a handle, and just like magic, water comes out. But behind that simple act is this massive, incredibly complex network. So today, we're going to trace that whole path, from the giant citywide system right down to the individual pipes inside a single building. Here's our game plan. We'll start big with distribution networks, then look at what powers them, gravity and pumps. After that, we'll dive into reservoirs, see how a house connects to the system, and finally, look at the plumbing inside a building. If you can nail these 5 topics, you'll be in great shape for your exam. Okay, let's kick things off with the big picture. You can really think of a city's water network like its circulatory system. We're talking about a huge web of pipes. These are the city's arteries, delivering clean, life-sustaining water exactly where it needs to go. So what makes a good distribution system? Well, it's a serious balancing act. It's got to supply water with enough pressure to reach every single faucet, sure, but also have enough power for firefighters to do their job. At the same time, it has to be affordable to build, easy to fix, totally safe from pollution, and sealed up tight so you're not losing water to leaks. It's a huge engineering puzzle. Now, this is really interesting. The layout of a city's streets often decides the type of water system it gets. For older, unplanned towns, you might see a dead-end system. It's simple, but water can get stuck and stagnate at the ends. A modern city with a grid layout can use an interconnected gridiron or ring system. This is way better because it keeps water moving and gives multiple paths if a pipe breaks. And then there's the radial system, which divides the city into zones, each with its own reservoir. Okay, so we have the layouts, the blueprints of the network. But pipes on a map don't move water themselves. So what's the engine that drives this whole thing? Well, it really boils down to 2 basic forces: gravity and pumps. The simplest, most elegant method is a pure gravity system. If your water source, like a lake up in the mountains, is way higher than the city, then its own weight creates all the pressure you need. It's beautiful, it's reliable, and best of all, it's practically free to run. But, most of us don't live next to a mountain. So for flat areas, you need this, the much more common combined system. Here, pumps do all the heavy lifting. They push water from the treatment plant up into an elevated reservoir, what most of us just call a water tower. That tower then acts like an artificial mountain, using gravity to give reliable, steady pressure to the whole network. It's the secret to making sure you have water even when everyone's taking a shower at once. Okay, pay attention here, because this is a classic exam topic: intermittent versus continuous supply. An intermittent system tries to save water by only running for a few hours a day, but there's a huge risk. When those pipes are empty, they can actually create a vacuum and suck in contaminants from the ground. A continuous 24/7 supply is way safer and obviously more convenient, but it means you need a bigger water source and a perfectly sealed network to prevent waste. So we've got water flowing through the city's arteries, powered by gravity and pumps. But, water demand isn't constant throughout the day. So how do we manage that? Where is the water stored? That brings us to the absolutely critical job of the service reservoir. You see, a reservoir is so much more than just a big storage tank. It's really the balancing heart of the whole system. It handles that morning rush hour of showers by releasing extra water, making sure the pressure never drops. It holds a critical reserve for emergencies, like fighting a fire, and it lets the main pumps run at a nice, steady, efficient rate instead of constantly turning on and off. It just makes the whole system stable. And these reservoirs really come in 2 main flavors. Over on the left, you've got a surface reservoir. It's basically a massive concrete tank built on whatever high ground is available. And on the right, you have the one we all recognize, the elevated reservoir, or the water tower. It's the same concept, but instead of using a hill, we build our own height with a steel structure. Both do the exact same thing: use elevation to create pressure. And it doesn't matter if it's on the ground or up in the air, they all share these key components. You've got an inlet pipe to bring water in and an outlet pipe to send it to the city. There's a float gauge inside, kind of like the fuel gauge in your car. For safety, an overflow pipe makes sure it can't spill. And really important, ventilators and manholes are there for air circulation and to let crews get inside for cleaning and inspection. Okay, we have traced the water all the way across the city and into the local pipe running down the street. Now, let's zoom in on that final, crucial piece of the puzzle, the connection that brings water from that public pipe right into a single house. The entire connection starts with this one small but super important part, the ferrule. You can think of it as a special, heavy-duty tap that gets drilled directly into the pressurized water main. This is the official starting gate, where water leaves the public system and begins its journey into your home.
Next up, attached to that ferrule is the gooseneck. And it's not just a funny name. That curved, flexible shape is a clever piece of engineering. The ground is always shifting a little, and traffic creates vibrations. The gooseneck acts like a shock absorber, protecting the rigid water main from snapping under all that stress.
So this diagram puts it all together perfectly. You can see the big city water main at the bottom. The ferrule taps into it. That little flexible gooseneck connects to the ferrule, and then that leads to the service pipe, which is the main line to the house. Before it enters the house, it passes through the stopcock, that's the shutoff valve, and finally the water meter.
And those are the last pieces you need to know. The service pipe is your personal water line. The stopcock is your control valve, your emergency shutoff. And of course, the water meter is basically the cash register, measuring every drop you use.
We've made it. The water has officially arrived at the house. So for our last section, let's just take a quick look at the different ways water is managed and delivered once it's actually inside the walls of the building.
Now, this is a really smart and common setup. Look closely. One pipe from the city supply goes straight to the kitchen. That's on purpose, so you get the freshest water with the highest pressure for drinking and cooking. All the other water gets sent up to an overhead tank first, which then uses simple gravity to supply all the other fixtures, like toilets and showers.
But what if your city supply isn't running 24/7? Well, then you need a backup plan. This diagram shows the solution. You add an underground storage tank. So when the city water is on, it fills up this big reserve tank. Then a small pump in the house can draw from that reserve anytime to keep the overhead tank full. It guarantees you have water even when the city supply is off.
And finally, for really tall buildings, even a tank on the roof might not be enough to get good pressure to the top floors. That's when you bring in the high-tech solution, a hydropneumatic system. Instead of relying on gravity, this uses an air compressor to pressurize a sealed tank of water. That compressed air acts like a powerful spring, actively pushing water up through the building with a lot of force. Okay, let's wrap this up. For your exam, make sure you know those 4 network layouts, the 3 different power systems, the functions of a reservoir, the 5 key parts of a house connection, and the 3 ways plumbing is set up inside a building. If you've got those down, you are going to do great. So next time you turn on that tap, maybe you'll see more than just water. Maybe you'll see the incredible, pressurized, and perfectly engineered journey it took to you.